Recording. Okay, so today 3.5 and 3.6 we're discussing complexity or efficiency, both time-wise and space-wise, and higher order programming.
Yeah, we're talking about performance and functions that return functions and take functions as
Well, it's a,
arguments.
it's we are talking about performance, but we are also talking about what do we mean by saying more performant.
Yep. Yeah, this chapter is actually pretty nice because it helps build intuition about how much things cost.
Yeah. So execution time. This is pretty like I think we should go through this, but this is pretty common in computer science anyway. Um, there are two parts to efficiency: execution time and memory usage. Using the kernel language and its semantics, you can calculate execution time up to a constant factor. The asymptotic time complexity of an algorithm is the tightest upper bound of its execution time as a function of the input size, up to a constant factor. So then we have this table, which, well, these are um, values for this is time efficiency in regards to these built-ins of the kernel language.
Yep.
Calculating the constant factor a priori is extremely difficult. This is because because of many reasons, right? So we have memory management. So uh, when we say memory management, we're talking about more
The
than
operating
just
s- yeah, or the operating system allocating pages so the program can actually use the memory.
um, yeah. We have the operating system. We have the hardware by itself. Like we have a piece of hardware that is intimately involved with memory management, and there is
Right.
also that.
Yeah, right. It maps the real addresses to virtual addresses when you do virtual memory
And
pages.
we also have caching. We also have concurrency. We have different sorts of architectures for computers. So there are many variables on this, and it's
And
probably
actually, even if none of that mattered, we still have the garbage collector of the language that you're using, right?
yeah. And then we have also like software problems such as the operating system, garbage collection, the language's runtime. We have many things. We have the context switching, right? Because our CPU is doing many times that like
It's doing
switching
more than one
context.
thing. Yeah, it's doing more than one
So
thing,
there are many
switching
reasons
between
why we
them.
cannot like trivially just say, okay, this is how we do the math. But anyway, we have the big O notation, which is also very classic, and be very careful about these equals.
It is not actually an equals, but people use it all the
Uh,
time for some reason.
oh, it's because um, when people are using the equals, they don't mean these like. This is essentially saying, oh, this is not a referentially transparently equals. Yes, of course, but nobody means that when they use this notation. But I agree that we should avoid ambiguity anyway. And this is the way that most people understand. Big O f of n is a set of functions that saying that Tn is of big O f of n means simply that this is a member of that set. So I think that's pretty okay. And then we have how you do the calculation on that. And here is pretty easy, right? We just compile the program. In this case, we're going to compile to the kernel language. And then we use the execution times to set up a collection of equations that contain this system of equations. We call these equations recurrence equations since they define the result for n in terms of the results for values smaller than n. And then we solve the recurrence equations. And that's
Yep.
what we use the table 3.4 for.
And there's the small caveat about unification, right? Because it may not actually be constant time depending on what you're unifying.
Well, yes,
But if
but
you're just yeah, but if you're just binding a variable, that's definitely constant time.
it's all about approximation. So if we approximate something to something else, and that is what happens most of the time, then we are okay eating the uh, uncertainty cost, let's say. But if the size of the thing, well, not necessarily the size of, but if we measure it wrongly, and that happens often, then we have a problem.
Yeah.
And then we have an example of the append function. So again, this is we translate this into the kernel language, which in this case is using a procedure instead of a function. And then we use the table 3.4 to understand which equation. And then you may ask yourself, who made this table, right? Allegedly, developers of the language, so they know how internally how the runtime works. They know how it is implemented, and you're just trusting that they did their job correctly. So this is how you translate each one of those kernel things into the mathematical equation there.
That is true, but if you reason about it, if you have a little bit of knowledge about how the hardware operates and how the language must use the hardware to implement its semantics, a lot of those are just like, yeah, this makes sense, you know?
I find that pretty hard because depending on what exactly is on the left, you're talking about, oh, I actually know that this is using a floating point dedicated hardware piece in the CPU.
But we're not talking about like, well, this table doesn't actually give us concrete times, you know? It just gives us, okay, this takes a constant factor, this takes a constant factor. It's not specifying the actual concrete number, but it's just saying it's a constant, you know?
No, 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 but not only that, it also has a max and it has these other things. And what I'm saying is that what you said, oh, you have a little bit of knowledge of the hardware. I don't think it's a little bit. There's a lot of, like, especially on x86, we're talking about very complicated things. We're talking
Uh,
about single instruction multi execution, like SIMD or something like that. SIMD? Is that how you
oh,
type that?
that. Yeah, no, but that doesn't like this is not the kernel language doesn't actually expose any of that. If you just look at what the kernel language exposes, it's like, okay, if X then else, right? And it says, okay, this takes a constant time plus the maximum of S1 and S2, which makes sense because you're checking a boolean and then you're jumping to S1 or S2 depending on the value, right?
Well, I guess if you are okay with like having like because you're gonna ask, okay, what is this? Oh, it may be a constant. Like, uh, so yeah, I see what you're saying. So like we can definitely reason like why this if translates to that. That's definitely true. But what I meant to say before was, okay, but what is these things? And what
Yeah,
are
no, if you
those
want,
things?
yeah, no, if you actually want to get an actual number for that, good luck.
Yeah, that sounds very not feasible at all. Anyway, then we do the math here. We can simplify it. We know that the input size of this is going to be equals to that because I guess, uh, well, how do we know that actually? We know that this is equal to that. Oh, it's because we are traversing that. Okay, that makes sense.
Yeah.
And we assume that this is that, so then we can simplify this into that. And then further simplifying, I'm assuming this is just doing some like, okay, we assume that we know the max out of those, and it's going to be that. And then we extract the constant again. So key 4 is born out of whatever manipulations we did with k1, 2, 3. And then we have this base case, which is essentially substituting 0 in here, which, well, it's going to be this, right? And
Yeah.
equality, or bind, is actually k.
Yeah. Yeah. Binding
Uh,
a variable is constant time.
yeah, and then it says two equations. What are the two? Are we talking about this and this?
Yeah. One is the base case and the other is the recursive case.
Yeah, but which substitution are we doing here? Because are we like how is K5 appearing here, right?
Uh, well, eventually, uh, n minus 1 is going to reach 0 at some point, right?
Sure.
Which means we need to get the k5 there um, when we eventually reach the base
Oh,
case.
okay. So that's true, but I think you can derive this by doing a couple more examples, like n equals 2 or 3. Then you're gonna recognize a pattern that requires the base case, So that's fixed by plus k5, and the repetition can be accumulated by times n.
Yeah.
That's fine. Yeah. So this is well, that's essentially what's written here. And then we also have a couple of a cheat sheet, right? So if you see these, the solution is already given to you because people already did the math. That's cool. And then I don't like this box because it's essentially saying that um, you can guess. Like this is something that you can learn with experience, essentially. You can guess from them.
And there's a technique you can use without guessing, but that's not in this book. See another book, basically, right?
You're talking about the generating functions.
Yeah.
Okay. And then you have another example of fast Pascal, right? And then we know that this is equal to that, this is equal to that. We go to the table, we derive that this is going to be the time efficiency equation. And then we do the same thing, but instead of 0, we go n, and then we use these two equations plus a couple of like handwritten cases to see the pattern emerging. And you see that this is essentially a second
Oh,
degree
it's
polynomial.
yeah. Um, yeah. See, there's this footnote on this page where it's saying, "Oh, it suffices to verify that a is not equal to 0," and then it says 12, right?
Yeah, if we
Uh,
guess this, then the actual solution is of the form this, and we will get a equals to 0. So if you assume it's a second degree, you can, and the actual solution is a line, we discover that the a is 0. That makes sense.
yeah.
Yeah, but like, this is what? I don't know, first year of engineering and every single mathematician course.
Yeah,
Um,
but this means if you overshoot on your guess, you're still fine actually. So it's more forgiving, I guess, I suppose.
that's true. Then we have another example of the merge sort. And then it explains again that, oh, but this one is interesting because in this case, we are actually using ceiling and floor. And then
Yep.
it gives you a trick to, well, it recognizes that this is tricky. So to get rid of that, we assume that n is a part of true to some k, because then we don't need to do the floor to ceiling anyway. And then you can just do some substitutions and do the series formula here, and then we encounter this, and then we conclude probably looking at the cheat sheet that is going to be n log n,
Log linear.
log
Not
linear.
terrible. Pretty
Yeah,
good
definitely
actually,
not
but
terrible. And then
not
we go to
great
the memory
either.
usage, and the memory usage, differently than the time, we have two kind of classifications. We have the instantaneous active memory size, which is usually what matters.
Right,
Uh,
it dictates how much memory you actually need for the program to work.
yeah, so um, well, not what you said is true, but I think we should be more pedantic. This is the number that gives how much memory the program needs to continue to execute successfully. To continue to execute successfully. So this is kind of like a snapshot. So the program is already running, and then you take a snapshot, and then you ask, okay, in the next cycle of the CPU, how much memory is required for this to continue? That's the instantaneous active memory size.
Yeah, there's the maximum active memory, which is the one I mentioned. I was thinking of that. I apologize.
Yeah, no, that's fine. But this is very important because this is actually the number that we care about the most when you are like developing software. So when you're talking about complexity with a coworker and we're talking about big O notation, we are usually implicitly talking about instantaneous active memory size. Because that means if you are if you are require more than what you currently have available, your program will just crash.
It's gonna
Segmentation
run
fault
out of
syndrome.
memory. Yeah.
The other value, instantaneous memory consumption, this is way less useful. I'm not saying it's useless, but I am saying that this is not. We are usually trying to optimize primarily the instantaneous active memory size, and then maybe in the third concern would be the instantaneous memory consumption, because this is the number how much memory the program allocates during its execution. So if you're running a Haskell program and you do some sort of profiling, this number can go into the order of magnitude of gigs. And then you may be
Yeah,
surprised. This is
it's allocation city.
this is just a fees bus program. How is this consuming gigs? Well, uh, it's because it's the total amount. It doesn't mean that it's the active amount.
It's just how much you allocate, even if it's just temporary data.
Exactly. So that's very important distinction. Here we have another table for that. And this is also very cool. So that these two numbers should not be confused. The first is much more important. A program can allocate memory very slowly and yet have a large active memory. So you have a gigantic area of memory that you're currently using. You're currently using to make your program continue, but you are using that very slowly. And a large in-memory database. Oh, that's the example. Like a large in-memory database that handles only simple queries. So when you spawn the database, it allocates probably a gigantic amount of memory and classifies it as active to continue. But the queries are simple, so you don't have to allocate even more. That goes very
Yeah,
slowly.
yeah. Basically, you have your the data in your database. It's just sitting there. It's taking up 100 megabytes. But then what you use to operate on that data is very little by comparison.
And the opposite is also possible. A program can consume a memory at a high rate and yet have very quite small active memory. So this would be what? A for loop?
For example, a simulation algorithm running in a declarative model. Quick example, game of life. You have to allocate the state at every iteration, right?
Yeah, that's why I said a for loop.
It's a for loop, yeah.
Um,
I mean, it's not any for loop. It's a for loop where you have to actually
I agree.
allocate, right?
I agree it's on any for loop. The active memory size can be calculated at any point during execution by following all the references from the semantic stack into the store and totaling the size of all the reachable variables and partial values. It is roughly equal to the size of all the data sources needed by the program during its execution. And then the total memory consumption. It uses a similar technique to the execution time calculation. Each kernel language operations as a well-defined memory consumption. We have the table. Using this table, recurrence equations can be set up for the program, from which the total memory consumption of the program can be calculated as a function of the input size. To this number should be added the memory consumption of the semantic stack. For the instruction bind, there is a rare case in which memory consumption is less than the mem size, namely when this is partially instantiated. Well, that makes sense.
Yep.
Um, we have more cheat sheets about, okay, so what are
How
we
much
talking
space
here?
each data type takes, basically.
Yeah, but is this what is
The
the
function mem size v is defined as follows according to the type and value of
yeah,
v.
but true of what? This is not written in here.
It's in the next paragraph after the
Unit.
list. All figures are
Oh,
in a number
number
of
of 32
32.
memory words. So these are not bytes, these are words.
These are words, yes. Correct for Mozart 1.3, apparently.
Um, yeah. And then we have amortized complexity. Sometimes not interested in complexity of single operations, but rather in the total complexity of a sequence of operations. As long as the total complexity is reasonable, we might not care whether individual operations are sometimes more expensive. Yeah, this is again an approximation problem. Section there gives an example of queues. As long as the sequence of n insert and delete operations has a total execution time that is linear, we might not care whether individual operations are always this. Yeah, so this is essentially saying
Yeah,
if you
if
have a sequence of operations and one of them is more heavily handed in terms of the complexity, we may ignore or like simplify everybody else because in the grand scheme of things they don't matter.
yeah, like when you yeah, there's the queue example from earlier that it mentions. Like in that one, the Okazaki queue, right, which is basically a pair of lists.
Hmm.
Sometimes you have to reverse one of the lists when the front of the queue runs out and you need to fill it with the back elements. And that's linear on the back list, but it's done infrequently enough that it doesn't matter that it's linear because by that point you already did enough constant time operations that like it evens out basically.
Yeah, but you said a second criteria. You said frequency. I said proximity. Hmm?
It's not really proximity, it's frequency because like for instance if you have to do
No, no, no.
Like if
I
you have
said
to,
proximity. I said that there is a sequence of operations, and one of them is more heavy-handed than everybody else, and we just ignore everybody else.
that's not quite it actually.
No, yeah, but that's what I said.
Yeah.
That's what I'm saying. What you're saying is different because what you're saying, which is what was said in the example of the queue, is that okay, we have this linear thing that happens very rarely. So we take that as a like this happens so infrequently that we don't care about it.
It's more like it happens infrequently enough that by the time it happens, you kind of already paid for it in constant time operations.
Exactly, exactly. And what I am saying is that if you have a for loop and you are doing three operations in the for loop, and one of them is like quadratic, and the other ones are like a particular, like I don't know what,
They would have
a particular line, so 3n or like 4n,
they
we
would have
just
to be
like
logarithmic. They would have to be logarithmic to do any kind of amortization, I guess,
I don't follow.
or maybe constant
It,
time, I suppose.
yeah, no, but that's what I'm saying. Not necessarily constant time like O of one, but maybe O of 100. Like what I'm saying is that it's very common when you have multiple operations, but you're trying to understand, okay, this for loop has which complexity? You have 3n, 4n, and square. You basically say that everything is a square, and then
No,
you
no, but
assume that that block
that's
is that.
that's normal, and it has nothing to do with amortization actually,
No, but I'm saying that this sentence reminded me of that.
which is fair.
So as long as the sequence of n operations has total execution time that is this, we monitor whether individual operations are always so like that's exactly what the example I gave. There are individual operations that have particular order complexities, and we might not care if they are actually constant O of one if we have the total execution time of linear, for example. So that's what I got
That's
reminded of.
well, yeah.
But I think I agree, you were right in terms of like the pedantic definition of amortized. It's what you said. It's about the frequency, not about the proximity that I was mentioning.
Well, it's like that last phrase in this paragraph, I think, is the key there.
This one.
Yeah,
If a sequence of n operations has total execution time of that, then we say that it has amortized complexity of this. That's fair enough.
yeah. Note the division by n at the end there.
Yeah. Uh, there are applications that this is not enough, and this is pretty obvious, right? So hard real-time systems, parallel systems, and interactive systems.
Yeah, you really
Hard
don't
times
want a,
real-time.
yeah, you really
Oh,
don't
not
want a
hard time.
spike of latency in those kinds of
Yeah,
systems,
people
right?
may die, so that's fair.
Literally, very literally.
A parallel system. I don't know if people may die out of that, but that's also a good case. The whole computation can only advance after all the simultaneous calculations complete. So you spawn a bunch of threads, all of them need to finish in order for you to proceed. That's another good use case for that. And interactive systems such as a game because uh,
You
the
don't want your
user,
game to just yeah, you don't want the game to just randomly freeze occasionally, right?
yeah, you definitely don't want that. And then we have, I never seen this nomenclature before, by the way, the banker's method and the physicist method. So these are methods um to calculate the amortized complexity. The banker
Yep.
method counts credits, where credit represents a unit of execution time or memory space. Each operation puts aside some credits, and expensive operations are allowed when enough credits have been put to cover its execution. So essentially, like every time you are fast than an expectation, we say that you have credits. And then when you are doing something a little bit sloppy, then we say, okay, you have to pay for that with the credits that you accumulated before.
Yep.
The physicist method is based on finding a potential function. Um, um, so this is a kind of a height above sea level. Each operation changes the potential. It climbs or descends a bit. The cost of each operation is the change in potential, namely how much it climbs or descends. The total complexity is a function of the difference between the initial and final potentials. As long as this difference remains small, large variations are allowed in between. So, yeah,
Okazaki
physicist
mentioned
method.
again.
Yeah. And then reflections of performance. Essentially, computers are fast, which is not new. So there's a very interesting thing here. the Cray 1, the fastest supercomputer in 1975, and it had a clock frequency of 80 megahertz
It
and
was
could
blazingly
perform
fast.
74-bit floating point operations per cycle, which is like very rather slow in today's standards.
Yeah.
And we also have the yeah, because of the situation, performance is usually not a critical issue. Um, essentially, like probably whatever you're trying to do, there exists an efficient algorithm for it. Um, which
Basically, if what you're doing is not fundamentally hard, as long as you're reasonable, you should be fine. Basically.
not only hard but also new, right? And there is a very low chance you're doing something completely unprecedented. Because sometimes you like, I'm gonna say sometimes, uh, um, at least once, somebody at some point in existence will find a problem that there is no efficient algorithm for this. Because well nobody tried that problem before. And then there's the what Marinho said about okay there are also problems that we already know but they are hard. So that's also something to keep in mind. Um, yeah, so we have then an NP complete problems. These problems are in NP. It is easy to check a solution if you have if you're given a candidate of a solution. Non-deterministic polynomial time. Okay. Most computer scientists suspect that NP complete problems cannot be solved in polynomial time. The performance of a problem can be insufficient if the problem is theoretically tractable. Then the program had to be rewritten to improve performance. We call that optimization. It is not optimal in any mathematical sense. Yeah, this is very good. This is very good
Yeah. Yeah.
because there is a tendency. Well, I'm not gonna say a tendency. I noticed that some people think that um, performance is what is the most important thing, and they are willing to trade anything, not only readability and maintenance, but also correctness or consistency, in order to achieve performance. But then it's written in here: optimization should therefore not be done unless necessary. Premature optimization is the bane of computing.
Yeah. Guys, premature optimization is bad. Don't do it. It's kind of sad that we need to say it, but there it is.
Well, but you and I, we are victims of doing that, right? So like,
Occasionally.
I wouldn't say occasionally actually. There is a lot of the time, especially in our projects, we actually strive for premature optimization. So, oh, let's use a finger tree instead of a list. Oh, let's use pointers to pass the game state because
Is it
pointers
pre-
are faster.
is it premature optimizations when you're just selecting reasonable data structures?
But what is the reason that you're selecting reasonable data structures? I could
Because
give
there,
another reason. Oh, because you can do pattern matching on lists, so let's use lists. The
the
library
reason
may
is,
be the library for manipulating lists may be good as well.
well, the reason is some operations we expect to do a lot. So let's select data structures that are reasonable, that have reasonable performance for those operations. For instance, it's very common to want to operate at the tail of a list, right? But if you're using a linked list, then that's suddenly linear. That's not a good idea, probably.
That's still for performance reasons. Well, everything that you said is it's because we some operations that we want them to be fast. Why? We haven't done profiling. We don't know that. We are going against this. But I know why we do that. It's because we already know that the trade-off is worth it. Like picking a particular data structure that have performant operations, it's not there's no diminishing point. We're not trading anything that we value. So for example, let's say that the Karata compiler used a lot of list pattern matching in the beginning. Let's say that. Let's say that not using this feature of this particular data structure in OCaml would be a huge pain in the butt. Then going for finger trees would be there would be a trade-off, right? So we are trading not being able to do pattern matching, and now we're gonna have to because we want the performance. Fair enough, but that didn't happen. We already knew before in the act of choosing the data structure, we already did the math of the trade-offs, and we settled to ourselves, okay, what are we gaining? Performance. What are we losing? Nothing. So why not? So that's the
Yeah,
catch.
yeah. You have to be mindful about what you're giving up for performance, right?
Exactly. But in our case, and I would say that this comes with experience and the nature of the project. So in our cases, I think every choice that we did in the past, they they were very fair choices because we didn't trade something that would be controversial or something
Uh,
like that.
Also, can I just say, I actually don't have a problem with linked lists in and of themselves, but depends on what you are using them for, right? If you have a finite list, then a linked list is actually not really the right structure because, like, if it's a finite list, it may be fair to say, okay, what's at the end of the list, right? Uh, I would actually be perfectly okay with using linked lists if I'm dealing with like potentially infinite streams, like
Yeah. We
the
we
classic.
saw that in the category for programmers book, right? The stream
Yeah.
data, the stream type. Yeah, I'm okay. Like I told you this before. I think the only reason that lists are still a thing, it's because they have usually a very nice syntax sugar in the language, such as pattern matching lists, and they have very useful standard library functions, utility functions.
But you could have utility functions for other data types. I think the real second reason is that they are that easy to implement.
But that doesn't matter. If you have a mature language, they being easy or hard to implement, it doesn't matter because that's not up to us. That's up for the compiler developers. So, for example,
Uh,
in OCaml, the batteries is already there, available. Everybody can use it. It's fine. It doesn't have the pattern matching though, and that's something that I value, in my opinion, right? The only reason that I would ever use a linked list are twofold. I don't have to use a third-party library, and I have pattern matching because I know that batteries library has pretty much potentially actually better utility list functions, right?
right.
So, like, that's what I'm saying. People that want to kill, for example, oh, we don't want strings in Haskell to be lists. Fine, just make all the conveniences of lists in another more performant thing. That's fine.
Again, well, there also depends on okay, what are you using? Again, I guess it goes back to is this a finite thing or is this potentially infinite, right? If it's potentially infinite, then actually I don't mind a potentially infinite string being a linked list. That's perfectly acceptable, actually.
I agree, but that's well, it depends on what you're using it for, like you said, right? But I feel that people sleep on this portion of the debate of like, okay, this was a mistake. Strings should never have been lists from the start. Are you sure about that? Because to me, it sounds like okay, you don't use the lists library, and you don't use pattern matching strings. So I don't know. But well, Marinho is right. It depends on what you're using it for. Depending if you need depending on your use
Like
case, that can be
like
completely
if you
fine.
could just say, okay, give me the standard input, and it gives you a list of characters, and that's fine because it's the interface it presents is just a potentially infinite Haskell list, which is lazy, right?
Hmm.
Um, that's actually correct because this is a string that you don't know exactly what is coming. It may actually never end if there's a long running process feeding it, right?
Hmm. I agree. Um, Optimization has a good side and a bad side. The good side is that it improves stuff, right? So, well, not only that, but the good side is that overall the execution time of most applications is largely determined by a very small part of the program text. The
Pareto
hard part
principle.
is finding it,
Yeah, yeah.
and this is not always true, by the way. Well, I guess it depends. This is written in such a vague way that it can be interpreted both ways, but sometimes it's a small portion of text that is distributed in many files or many functions. It's this line and that and this one and those. These all of these combined and make the performance be poor. So finding them not only means finding them as a whole, but finding them a grouped or not grouped. They may be like distributed in the program.
Yeah, it's like finding a needle in a haystack, except the needle is atomized and could be in 5 different places.
Exactly. This spy should be identified after the application is running and only if a performance problem is noticed. If no such problem exists, then no performance optimization should be done. Well, this is called profiling. Reducing a program's space use is easier than reducing its execution time. The overall space use of a program depends on the data representation chosen. If space is a critical issue, then a good technique is to use a compression algorithm on the data when it's not part of an immediate computation. This trades space for time. Makes sense. It's going to be compressed, so it occupies less space, but now we're going to have to compress and decompress, so that's going to use time.
Yeah.
And now we go to higher order programming. So this means receiving procedures or functions as arguments.
Yes.
A procedure is of order n plus 1 if at least one argument is of order n and none of higher order, right? And then I didn't know the names of these things, so I'm very glad now I know them. We have four basic operations. This is not done in like this is not an operation that you use in programming per se. These are more operations that are available to you in the language. And sometimes, at least to me, I didn't even know they had a name. So procedural abstraction. So let's say that you have a value, I don't know, enclosure, like a map, but you wrap that map in a function that receives nothing. That's procedural abstraction. The ability to convert
Uh,
any statement into a procedure value.
right. If you have like not really just a value, it could be literally any statement, right? It could be a raw value, could be an if,
Could be many things.
could be many things. The point is, whatever it is, you can put it in a function.
Yeah. Genericity, the ability to pass procedure values as arguments or procedure calls. So this is more like the higher order thing. Instantiation, the ability to return procedure values as results from procedure call. And we saw a very interesting example of this in Zig, right? Because this is cursed in there. And then
Yeah,
embedding, the ability to put procedure values in data structures.
yeah, all four of those can be very useful if they are used for the in the proper occasion, right?
Yeah. So procedural abstraction. So we also call this having a statement packaged, right, into a procedure by wrapping the statement into a procedure body. This does not execute the statement, but instead creates a procedure value, a closure. Because the procedure value contains a contextual environment, executing it gives exactly the same result as executing statement. Um, why is that? It's because you may have the procedure definition, the procedure definition in a particular part of the code that have surrounding things, but because it has its own contextual environment, a closure, it's executing it gives exactly the same result as executing the statement.
And this is why lexical scoping is important.
Exactly. The decision not to execute the statement is not made where the statement is defined, but somewhere else in the program. And then either executing, so figure 3.20 shows the two possibilities. We executing the statement immediately or with a delay. Because you can think that wrapping, doing the procedure abstraction is actually doing some sort of laziness. So like you can actually delay on executing such statement, and you can control when that's actually going to be executed. Procedure values allow more than just delaying execution of a statement. They can have arguments, which allows some of the behavior to be influenced by the call. That's true. And then it underlies high order programming or object oriented programming, and it's extremely useful for building abstractions. So here we have an example of solving a second degree polynomial equation. And this is using uh, hard-coded values for the ABC constants. And then we can actually put them as arguments and do this and basically make this more useful for other types of
Yep.
equations.
Yep.
And this is an example of that. And then a common limitation. This is where, like, I actually maybe I have questions about this. Many older imperative languages have a restricted form of procedure abstraction. Let's look at Pascal and C. In C, all procedure definitions are global. They cannot be nested. So are we talking about making a function inside a function?
Yes, you cannot do that in C.
This means that only one procedure value can exist corresponding to each procedure definition. That's true. In Pascal, procedure definitions can be nested, but procedure values cannot be used in the same scope as a procedure definition. So that is essentially functions inside functions.
You can have function inside functions, but the implication of this, well, it says in the last line of the paragraph, right? The last sentence. It's you cannot actually return a procedure because of this restriction.
Ah, okay. So you're saying that I can define it, like I can define an internal function inside of another function, but I can't return that because it can only be used inside the body of the outer one.
Yeah.
Okay, I got it. This means that many high-order programming techniques are impossible. For example,
Oh,
in
by the way, this has a name. It's called the Funag problem. Look it up sometime.
what I said has a name.
Yes, it's the Funag problem.
Okay.
Short for
Well,
functional argument. Like, there's a whole bunch of
Funag
literature about this. If
problem.
you, yeah,
Refers to difficulty implementing first-class functions in programming language implementation so much to use stack-based memory allocations of the functions. Okay, cool. It is impossible to program new control abstractions. Instead, each language provides a predefined set of control abstractions, such as loops, conditions, and exceptions. A few higher-order techniques are still possible. For example, the quadratic equation example works because it has no external references. It can be defined as a global procedure in C and Pascal.
hello, Nathan.
Here, Nathan. The restrictions of C and Pascal are a consequence of the way these languages do memory management. In both languages, the implementation puts part of the store on the semantic stack. This part of the store is usually called local variables. Allocation is done using a stack discipline. Some variables are allocated at each procedure entry and deallocated at the corresponding exit. This is a form of automatic memory management that is much simpler to implement than garbage collection. Unfortunately, they create dangling references. It's extremely difficult to debug a large program that occasionally behaves incorrectly because of a dangling reference. Um,
Yeah, and that's why. That's why.
in both C and Pascal, creating a procedure value is restricted so that the contextual environment never has any dangling references. There are some language-specific techniques that can be used to lighten this restriction. We're going to see that later, apparently. We're going to see that later.
Yep.
Genericity. So this is essentially the core thing out of the higher order programming, which is the ability to pass functions to it. And we have seen this before with the iterate control abstraction, that you can pass procedural arguments such as transform and is done.
Yep.
Um, we say that the entity is abstracted out of the function body if you make that an argument. The specific entity is given when the function is called. And we have the sum list example here. And we can change this, tweak this, to passing the 0 and the plus as arguments. And then congratulations, we made a fold. And it's a fold R because it associates to the right.
Can I just say that the argument names are kind of funny?
L, F, and U.
Yeah. Specifically because they are in this particular order.
Le flou. No, le fou.
No, no, yeah, because we have FU, you know.
And then we have another example of the fold R to define other functions on lists. And then we can rewrite the merge sort example using that instead. This puts definitions on merge and merge sort inside the new function. This avoids passing the function f as an argument to merge and merge sort. And then yeah, we can write it like this now because well, we are passing a lambda here.
This kind of thing is useful. Oh, this particular example is useful if you have if you want to use a custom sorting function, right?
Yeah, and then we
Uh,
have instantiation, right?
yeah.
Which is essentially like, okay, pass me the function to make the sort, and I will give you not a function that is gonna utilize the function that you're giving me.
Yep.
And we say that calling make sort instantiates the specification. It returns an element of the set which can call an instance of the specification. And then finally we have embedding. Procedure values can be put in data structures. We have explicit lazy evaluation, which is also called delayed evaluation. That is, well, this is exactly one of the examples that Marinho said earlier. So you have a data structure that grows, and I give you the part of the data structure and a new function to calculate the next portion of it. And we also have
Yep.
modules. A module is a record that groups together a set of related operations. And we have a software component, which is a generic procedure that takes a set of modules as input arguments and makes a new module. This is a functor, right?
This is basically an ML functor, yeah. Except because it's OS, it's dynamically typed. But yeah, it's essentially the same thing.
Okay. Um, um, cool. And then we have examples that we're gonna see in the text a little bit later, but this is essentially a for loop, and
Yeah,
this is
the integer version and the list version, right?
yeah. So this is like what the boundaries and the increment function
The
and
increment amount actually.
the increment amount. Um,
And then
and
the body of the loop is the P.
yeah, weird choice. This could be like
It's a procedure, right? But yeah.
that's fair, and this is essentially map, but actually this is for each. If you're gonna be completely like pedantic in here. And then we have loop abstractions, right? So as examples, in the previous sections, loops are in the collective model tend to be verbose because they need explicit recursive calls. Loops can be made more concise by defining them as control abstractions. There are many different kinds of loops you can define. And then we have the integer loop, which, well, does exactly what we said before. You start from A, you go to B, you increment by S, and you call P each time. And these actually has the flexibility of going loop up and loop down, which depends on the sign of the increment value. And we also have the list loop, which essentially does the for each. And then we can upgrade them again to use accumulator loops. The for and for all loops just repeat an action on different arguments, but they do not calculate any result. We can fix that by adding accumulator to the party, and we're going to be doing that by using folds, because of course.
I mean, what did you expect, right?
Because of the freaking course. And this is actually pretty cool because it's using the data flow variables again. Essentially, it's creating a mid variable in the middle of the process, calculating that, and then passing it further on the line, right? And this
Yep.
list is always shrinking, which means that at some point the answer is going to be equal to the input.
Yep.
So that's pretty cool. And then we have the difference about left fold and right fold. So the left fold, you start the parenthesis nest starts from the left and then it grows, and the fold R does the opposite. So it's the parenthesis nesting, the associativity starts on the right and then it grows to the left.
Yep.
And this is how it's gonna look like. Um, and then we're gonna have fold L and fold R. And we also have this U element. This makes them easier to calculate, and to do this, we add a neutral element.
Yeah, the idea is okay, let's try to make it so we actually only take one element from the list per iteration, right? Because otherwise, the first iteration is actually going to take two elements, which is non-uniformity in the algorithm, makes it a bit harder to write.
Oh, you mean like this is a function that is taking two things.
Two things from the list, yeah.
Yeah, but this is actually pretty confusing because usually this is the accumulator of the fold, right? This is the current accumulator and the element of the thing.
Right, but the point is the U in this case is the initial accumulator.
Exactly, but nobody calls that the neutral element.
Well, it typically is the neutral element most of the time, right? If you're like adding numbers, you typically use 0. If you're multiplying,
I
you use
agree,
1.
I agree, but I
It
think
doesn't
it's
have to be though. Yeah,
exactly. I
it's a
think
bit.
it's less general with no gain.
Yeah,
Well, not that there is no gain. I think it would be better from an educational standpoint to just say that this is a like neutral element or, and then in parentheses, and most often, the initial accumulator. And then this is a pictorial representation of this process. So we have the fold L on the, yeah, this is fold L on the left, and we have fold R on the right.
actually, those are both fold Del. It's just that the left one is accumulating using integers, you know?
Wait, so am I confused? Yeah, I'm confusing the pictures. This is the picture that I wanted to.
Yeah, that's the other one. That's the picture
Yeah,
you're
my
thinking
bad.
of.
Yeah, this is exactly what Marinho said. This is the integer, and this is the. Wait, yeah,
This is
this is the
fold
integer
L.
version, and this is
This is the list version.
the list version.
Yeah, yeah. The text actually mentioned this, right? Fold L is just another name for this for all H on the right.
Yep. And then we see the difference between fold L and fold R. Yeah, so the arrow goes here, back to the left, and this one it grows to the left, starting from the right.
And also note that the X's go in opposite orders as well.
Well, but this is because the fold R needs to do a reverse. We're gonna see that later in a bit.
Yeah.
Okay, so iterative definitions of folding. So figure 3.24 defines for all ACC in an iterative manner, and the fall also fold L. Here's the same definition in functional notation. So the 3.24.
Yeah, this one. It's written as a procedure, right? The for all X.
Um, yes, it's written as a procedure, that's true. And it's using the data flow variable streak, as I said. And in this one, we just tail call.
Well, the other one is also doing a tail call. It's just there's some stuff before the tail call that is implicit here, but there is written out explicitly
No,
up
but that's why
there.
I said in here we just tail call. We don't do
Yeah,
anything else.
yeah.
This is compactor than the procedure definition, but it hides the accumulator. Yeah, I see no sense in this sentence. I read that many times, and I was like, what the fuck are you talking about? It's
It
exactly
hides
here.
it hides the variable that is being passed, I
Oh, so
guess.
it
But
hides
like,
the accumulator of the next iteration. That's what you're saying, which is
yeah,
this. Yeah, but that's not very. This was poorly written in my opinion, because what are you talking about? It's literally right here. But I guess what it meant to say is that the next iteration accumulator, which is this, is hidden. It's which actually that's also not the right word. It's nameless.
it's anonymous.
Yeah, compactness is not always a good thing. What about fold R? The discussion on genericity in the previous session gives a recursive definition, not an iterative one. And then how do you do that? And this is how you do that,
You
right?
reverse the list, which is, well,
Yeah,
it's
but
basically trading time for
yeah,
space
but
in this case,
yeah, but
but
I'm a little bit confused. Yeah, I'm definitely confused because it's saying that can you give an iterative definition of fold R? This is not one, right? This is just doing a functional one.
no, this is iterative.
How come?
It's tail calling.
So this one
The
is also
point is
tail
that,
calling. So
yeah, but that's foldel, not foldar.
yes, no.
The,
The
the
names are
point is that
different. Go for it.
No, the point is that the original definition of foldar that it gave up there, like when it introduced foldar for the first time, is not actually iterative because it doesn't call itself in tail position. Like way back when it introduced
But
recursion,
that's
I
not the
guess.
definition that we're using here, man. Let me backtrack. I think we are confused. I'm not explaining myself properly. Let me try to clarify. So it starts the session saying, here is the same definition of for well, it's saying here that the previous definition of foldel, which is for all ACC, is iterative, and then this is the functional one. And then
It is
what
also
are
iterative, yes.
yeah? Wait, repeat that.
Foldel, both definitions are iterative. It's just that one is written as a function and the other as a procedure.
Oh, okay. So you're saying that this is iterative and functional.
It's using functional notation, yes.
Okay. Okay, but
Okay,
then
let me
this is
let me try
not
to.
a dilemma. We're not saying that you are either iterative or
No, 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 no,
functional.
no, 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 no. It's talking about the thing that it's talking about. The thing that it's talking about not being iterative is the fold R, not the fold L, because like
Where the
the
heck is
definition
the
it gave
fold
earlier,
R?
it's in 3 point. It's a bit earlier. Software component, blah blah blah, merge sort.
Here it is.
There. Yeah, that's clearly not iterative, right?
The next one is also not, to my eyes.
The
That's
next
what I'm trying
the
to
next one
understand.
the next one actually is though.
That's what I'm trying to understand. Exactly.
Okay.
So what are the definitions we're using here? Because we are saying that this is not iterative. What is this doing? This is doing a tail call, and this is calling itself. What are
No,
the
no,
other
but
things
no,
noteworthy
no,
in
no, no,
here?
no, no. It's not iterative because the tail call is not itself. It's tail calling something else and calling itself in non-tail position. It's growing the stack, so it's not iterative.
Oh, okay, I see. That's what I was mistaken. This is the tail call is actually something else aside from the foldar.
Yeah,
The stack is growing in here.
yeah,
And in the new definition, which is this one down here, this is because loop is being called in here. In tail call position, hence the stack is not growing.
yeah. This is just another case where it's like, dude, you're using the wrong data structure. You have to do a reverse in order to get an iterative folder. What are you doing?
Yeah, no, but I was mistaken. This was my confusion. I was just taking a look on. Okay, we are doing a tail call, and we are not doing the bind because what was like triggering to me of the fold L is that this is doing the bind with the mid, right? For some reason
Yeah,
that was the difference that I got in my mind. But what is actually the point is the stack growing. So you're
yeah,
right. Linguistic support for loops. So well, we can make our lives easier by adding stuff to the language using these built-ins. So we can have fors in the case of integers, and we also
yeah.
can
And
have
the
the
point,
false, right?
yeah,
So
the point is that these could theoretically de-sugar to the procedures we were just talking about, right?
exactly,
In the actual implementation, they probably don't because of efficiency reasons, but they could in principle, right?
exactly. They could in principle. And then declarative versus imperative loops. That's actually a very. I think we should read these two paragraphs. There's a fundamental difference between a declarative loop and an imperative one. A loop in imperative language, we are using the from C or Java. Um in those ones, the counter is an assignable variable which is assigned a different value on each iteration. The declarative loop is quite different. On each iteration declares a new variable. All these variables are referred to by the same identifier. There is no destructive assignment at all. On first glance, this is like obvious. Of course, that's how that works. But there are major consequences of such difference. The iterations of a declarative loop are completely independent of one another. Therefore, it is possible to run them concurrently without changing their loop's final result. This runs all iterations concurrently, but each of them still accesses the right value of I. Putting the statement inside of a statement thread runs it as an independent activity. Doing this in an imperative loop would raise havoc since each iteration would no longer be sure they access the right value of I. So, the increments of the loop counter will no longer be synchronized with the iterations.
Mutation making concurrency harder. What a surprise.
Exactly. And then we have the list version of the for.
Can I just say for a moment here that, like, I wish the Python folks had read this book because you can clearly see that X should not be bound after you return from the for all expression, right?
Yeah, yeah. And then we have patterns as well, more convenience for us, allowing you to hook an accumulator into it. So this is the collect C here.
Yeah, and then it mentions that, yeah, in order to do this seating works, it actually uses explicit state under the hood, and
Yeah,
it
explicit
also
state.
mentions, yeah, look at Common Lisp's loop macro if you want to know more about loops, which is fair, but also is a weird thing to suggest. But okay.
Yeah, no, but there is a gotcha here. How can we do this without threading the accumulator, right? Because if you can thread the accumulator, then we don't need the explicit state at all. We just pass it along, right?
Yeah,
But we're not doing that. We're not doing that. And that's why we need explicit state. And yes, the common Lisp recommendation is weird. And we also have other built-ins for how should I
yeah,
say?
break and return and continue. Those are other things that are typically used together with loops if you're using
Exactly.
imperative languages, right?
Exactly. And then we have data-driven techniques. A common task is to do some operation with big data structure, like folding or mapping, and we can do that. So now we're implementing map, which, by the way, this is using a foldar to implement a map, right?
Actually, not quite, because of how the construction of the list pair is desugared. The map is actually a tail call here. So, is it a foldar? It kinda is, but also it kinda isn't because it has different space usage.
I don't follow. It is the map is defined in terms of a foldar, so it is a foldar.
Well, it can be defined with a foldar, yes, but the definition above is slightly different
No, no,
because
no.
the
This
map
one
is a.
is no. This is how I would implement it, and I'm a very like naive man, right? I think I would be crucified. I would die in a crux like this
In a
if I
cross.
set in a cross, sorry. Um, if I implemented like this, because everybody would say, oh, you should use foldar because of the loop fusion, whatever. And this is
Ah,
how.
I would actually argue in Oz specifically, you should use the definition above because then map is in tail position, that recursive call.
I keep having to remember. This is misleading because of the whole disfiguring thing.
Yeah.
Okay, that's true. But it can be defined in terms of the foldar, and then if you're asking yourself how come, the answer is in who is doing the cons. What is going on in the cons here? If you pick a piece of paper and you write this down, because we are doing the cons like this, um, I think it's actually gonna
Yeah.
be fine. Because the foldar is also doing a reverse inside, right?
Well,
So there's a
depends. We
reverse.
would we would have to, we would have to look at the actual implementation in Oz to answer that question, but it could just be doing a reverse inside, which would make it sad, but it also would make it not take extra space. So I don't know. It's kind of a
No, but
toss up.
I think like if you don't take into account how the cons is being done and the reverse, this foldar is kind of nonsensical because you're mapping and the output will be the other way around, right?
That would be the case if you have been using a foldel, not a foldar.
On a map?
Yeah, if you try to define a map using a foldel, you end up mapping the reverse of the list. That's the answer to the question on the next paragraph, by the way.
Yeah, no, yes, but yeah, I think I am confused because to me it's more intuitive to implement a map using a foldel because it's from left to right, right?
The problem is, okay, you're using a foldel. That means you're consing inside of the arguments to the foldel, right? Because you're passing an empty list as the initial accumulator, and then
No,
you're
no, no,
just
no, no.
consing.
But that would not be the. How can I say this? This lambda will have to change, right? Because this is an element and this is the accumulator, right?
Doesn't matter, you can flip the arguments. The point is, if you use a foldel, you have to call a reverse afterwards.
Yeah, we can play with that after the session because to me, I implemented maps with foldels before, and that's very okay. Like, am I tripping balls in here? I don't think so. I really don't think I'm tripping balls. I really like because foldar will do the reverse, right?
No,
It
no.
will start.
Foldar,
Go on.
it depends, right? Foldar will either do the reverse before entering the loop, and then it can be tail recursive, or it's just not tail recursive and doesn't do reverse. But either way, it starts accumulating the new list from the right, is the point.
Exactly. So it starts from the right, right?
Yeah,
So this is gonna be the first A, right? So this is new, and then this is gonna be the last element.
yeah.
Yeah. So the output of this will be the opposite.
No, it won't, because when you do a cons, you're adding an element to the beginning of the list.
I think I see. Because in the next iteration, we're gonna have what? New in the last, and we're gonna have the second to last in here. And
Yeah,
then in the next, we're gonna have the second
yeah,
and
yeah,
the
yeah,
last and
yeah,
new and the third to last.
yeah,
I see.
exactly.
I see. I see. Makes sense. Makes sense now for me. Yeah, to me the fold only makes sense if I don't use this function. I would use something else. Filter, of course. This is pretty classic, right? You have a predicate, you pass a predicate. If it's true, you keep it. If it's not, you don't. And then there is the you can implement
Yeah,
filter
if,
itself in terms of the iterate.
yeah,
It
you
looks
can do
ugly
that.
as fuck, but you can.
You can, yeah.
And then we have the tree-based techniques. Then we have the DFS and the BFS.
And there are lots of ways to pass the accumulators around, so there's
Yeah,
more than just fold down
yeah.
and fold
You
down.
bottom up, you top down, and the bottom up you do the children, and then you do the parent, and the top down you pick the parent, and then you go down. So all of these things are explained in here. Pretty normal stuff, right?
Right.
Nothing to create, and you can use the fours in this case, right? So for each of the sons, you do the DFS, and the order that you're doing this, if you're calling the LLF in the beginning or later, that changes if it's a top-down or bottom-up approach.
Yeah.
Very easy to change.
Yeah,
Um,
explicit lazy evaluation. It doesn't go too much. It doesn't actually give code examples here, but it's what we've been talking about. You just package the statement into a procedure
exactly,
and you call it later or
exactly, and
don't.
this is also called demand-driven, right? So
Yeah. And it does give a slight spoiler that later on we'll see how to do it using the Oz data flow variables, because they actually support triggers, which are very nice.
and then it
Ah,
repeats itself about the whole. I send you the current element in a function to create the next one.
yeah, it's just in one case you have a function if you're doing it explicitly. In the other case, you just have a variable that when you use
Mhm.
it, it's going to trigger the
Mhm.
function
Mhm.
call.
Mhm. Yeah. Yeah. Yeah.
I have things to say about that, but I can wait until you actually see it in the language in the next chapter.
Oh man. Okay.
Not the
That's
next
good.
chapter, the one about laziness, actually.
Yeah. Exactly. I just noticed. I think the foldel would use a concat, right?
Yeah, and then the concat would be terrible for performance.
Yeah. No. The reason that I'm saying this is because okay, I'm gonna mention because Magarin is gonna hate it. But I think that's
Uh,
why my mind was saying foldel is because okay, this lambda will not use a cons.
Funny thing though, you can actually implement a map as a foldel or reduce enclosure if you use vectors, because conj puts an element at the end, not at the beginning.
That's true. But yeah, but I'm not being well. I am stupid, but not because of this. This is definitely doable with a foldel, but you would be using a concat in there.
Yeah, either that or you do a cons and then you have to call a reverse
Reverse it
afterwards.
afterwards. Yeah. And then currying, which is just to say that you are doing partial application of the functions, right? So in this
Yeah,
particular case, you want to, well, what's the example here? Lower bound 10, so you partially apply 10 to the max function, but in language, but this only is only like syntactically convenient in SML and Haskell like languages. In here, you have to do it that yourself, such as written in these terms.
Yeah, like that, or like the one below, right, where max is not actually curried, but you can partially apply it
Exactly.
like this.
Well, partially, it's not partially applied because you are applying all of it. It is just that the y is coming from from above.
Well, you could say that lower bound 10 is a partially applied version of max, can't you?
Yes, but I think that's more true, like more true, whatever that means, in this other version. This
Yeah.
is more like you have an auxiliary function that it has a better name, but max is actually completely fine, like completely applied, let's say.
Yeah, and that's about it for this chapter, basically.
And that's what we have for today. So what are we going to be reading next time?
We're going to be going over abstract data types.
Yeah, but I want to kind of to know. Okay, so 197. We can go 187 all the way to. I think we can finish chapter 3. What do you say?
Uh,
233. So that's 34 pages. No, 36 pages. I think that's okay. What do you say?
that's probably okay. That's probably okay.
Cool. I'm gonna finish the recording now.